Remember with integrals that we are working backwards from a derivative. A big clue on how we can solve this problem is to actually do a little bit of trial and error. Do you remember your derivatives? Let's say, for example, that you are taking the derivative of y equals x squared. What would you do? Well, this one would involve bringing the 2 in front of x and taking the original power, which was a power of 2, and reducing it by 1. So you get 2x at a first, or simply 2x. The same thing goes for y equals x cubed, right? You would take the 3, that's the power of x, bring it in front, and now reduce the power by 1. So if for derivatives, we are always reducing the power of x by 1 and bringing in a constant, when we're working backwards with integrals, that gives us a clue on what we're actually going to integrate. The final answer we're going to get is going to have two properties. Integrating something will simply have a power of x that has a value that's 1 more than what it used to be. And 2, we need to make sure that we correct any multiplied coefficients. And what do I mean by correct, right? Notice how on the right-hand side, when we're taking derivatives, anytime you derive a function, your answer is going to be a multiple of the old one. But with integrals, when we're working backwards, we're actually doing the opposite. Sometimes we need to divide or undo the function so that way, when you're determining whatever it is your answer is, you're not going to have an answer that's a multiple of what it should be. With trial and error, we know now that when you integrate x to the n, your final answer is going to have something where you'll have this x to the n plus 1 term in here, but we need to see what it is we're going to have that's the leading coefficient. With some trial and error, let's try the following. Let's try just taking the derivative of y equals x to the n plus 1. When you take the derivative of this, it's no different than what we did above. The only difference now is the power of x has an n term in there. But it's the same thing because you're simply going to bring that old power in front as a coefficient and then simply reduce the power of x by 1. With that being said, also notice that with this n plus 1 term that's in front of x, that is a constant. Remember that with derivatives and integrals, anytime you want to derive or integrate something, you can actually bring the constant out in front. So in other words, if I am taking the derivative of, let's just say 3x squared, it would be the same as 3 times the derivative of x squared. We can use this concept to help us out when we're trying to integrate the original problem I gave you. But the thing is that because we're working backwards here, a big hint is that we're going to have to correct our trial and error answer by dividing by something instead of multiplying by something. If we want to find some original function such that for that original function, when we take the derivative of it, we have a 1 coefficient in front of this original problem giving you, what should we do to correct our guess here for x to the n plus 1? In other words, what should we multiply or divide it by to essentially undo any coefficient that may have been brought in from taking the derivative of whatever parent function we're trying to find? I'll give you a hint. Think about reciprocals. Pause the video and see what you come up with. Okay, so if you gave this a thought, you'll have noticed that to correct our answer, if the derivative of this parent function x to the n plus 1 gives us this n plus 1 coefficient term on the right that's now being multiplied by everything, but in the original problem I gave you, the coefficient was actually a 1, then to undo this, we need to simply correct this by dividing by n plus 1. This means that, rewriting the original equation above, the derivative of y equals the integral of x to the n dx is going to be 1 over n plus 1 times x to the n plus 1. Is this our final answer? Not quite, because remember that when we take the integral of something, we are actually coming up with a family of functions. If this right here is some original parent function where when we took its derivative, we came up with this original problem I gave you. The problem is that if the original function here had a constant that was added to it, we lost a bit of information. Why? Because when you take the derivative of a function plus a constant, it's the same thing as taking the derivative of the function plus the derivative of the constant. And we all know that the derivative of a constant is 0. Therefore, we need to actually make a correction here. This means that we need to add this plus c term at the end of our answer. And this is what you get when you integrate x to the n dx. Go ahead and give it a try. Your homework is to take this final answer, 1 over n plus 1, x to the n plus 1, and then plus c at the end of it. And when you take its derivative, you should find that you are going to come up with an answer that is simply x to the n dx. And I hope you liked what you saw in this video. Hit that subscribe button if you haven't already. And be sure to check out this video where I give you an example problem so that this problem that we're showing here for integrating polynomials can be applied to x cubed. And I hope you have a great day.